Okay, so this is the next video on Earth-like support systems. So this covers section 3B of the specification and is primarily about short and long-term changes in the water and carbon cycles. So short-term changes are considered to be ones that last a day or seasonal, and then long-term changes are over many years, so potentially thousands of years. So specification wise, we've got short-term changes to the carbon cycles and the significance of these changes, long-term changes to the stores and flows, and then we'll also look at how these changes can be monitored and we can research these changes over time. So something to be aware of in terms of wording here is that we've got the term significance. So a very straightforward question you could be asked is to examine the significance of these changes, and that would ask you to be evaluative about how major those changes are. So you could look at some examples of short-term changes that are pretty insignificant and compare those to, say, longer-term changes such as glacial periods. And anytime we're looking at significance of change in that way, you want to put it in terms of the flows and the stores within the cycle, because then it's demonstrating knowledge of the cycles as well as knowledge of the changes. So you can kind of make reference to the atmospheric store, and you can make reference to the magnitude of evaporation taking place, so how much evaporation is taking place. Okay, so that's how we can look at the specification and understand how we will be assessed. So, first of all, short-term change. We've got this term up here, diurnal. So you may or may not have come across this previously, depending on what subjects you study. But diurnal basically means daily. So it's the day and night cycle, 24-hour cycle. So we have here a graph showing CO2 every hour over a day. And this is over a number of years. This is sort of the average for this time period in this place. So it's not just a sort of one single day, but an average over time. And we can see that we go from a maximum of around 425 parts per million in the atmosphere at about 2 o'clock in the morning, 2 a.m. And then we drop down to 390 parts per million by about 2 o'clock in the afternoon. So have a little think, what could be causing that? So what processes are occurring which is causing the amount of atmospheric CO2 to drop by roughly midday and then rise again as we go later into the evening? So primarily what's going on here is that at this time of the day, the sun is up and we're experiencing a large amount of photosynthesis. And this process is removing CO2 from the atmosphere, and it's being sequestered and held by plant life. Okay, so plants are growing during that time, they're removing CO2 from the atmosphere. And then as we come into the nighttime, into the evening, that stops, and plants actually respire at night. So we often think of respiration as an action that's carried out by animals, but plants respire also. It's just that plants photosynthesize more carbon than they respire. So on balance, plants have a net positive effect in terms of removing carbon from the atmosphere, but they do also respire. And at night is when they're doing that respiration. That's how they get energy at night. Okay, so that's what's going on here. And we can see that it's not an insignificant change. We've got roughly 35 parts per million difference between day and night, but it's obviously kind of changing backwards and forwards each day, and it's not a permanent change. So in terms of significance, it's realistically not having a major effect on the atmosphere. It's not kind of necessarily having a huge impact there. Okay, so daily changes to the water cycle. In a similar way to what's happening with the carbon cycle, we're going to see similar changes to the water cycle. So how will the water cycle change between day and night? What flows do you think are going to increase during the daytime and might decrease at night, or vice versa? So evapotranspiration, that is I think obviously going to be at its highest during the middle of the day when the sun's energy is evaporating moisture. So the magnitude of evapotranspiration flow is going to increase during the daytime, and it's going to be very low at night. There's not going to be energy available at night. We also, therefore, say, for example, during the summer, you might have experienced um, thunderstorms happening quite late in the day. So that's largely due to lots of evaporation happening during the hot part of the day. And then as we get into the evening, there's a huge cloud that forms and we get heavy rainfall. So that's again being affected by daily cycles of sunlight and energy. We also get other things that happen at specific times of day. So dew forms in the mornings and during the night when it's cold. So if you sort of leave things outside overnight, they kind of get damp, they get soaked in dew. So there's all kinds of things that are happening on a sort of day-to-day basis. So like I mentioned, we've got convectional rainfall happening during the daytime. So that's the rainfall where we've got the ground and we've got the sun, and the sun's energy radiates to the ground, it warms the ground. This leads to air rising, clouds then form, and we get rain. Okay, so that's convectional rainfall, and that's directly affected by the sunlight and the sun's energy that's happening during the daytime. This is really quite particularly relevant in the tropics. So in the tropical rainforest, there's a daily cycle of rainfall. So every afternoon in the rainforest, there will be heavy rainfall because of convectional rain. So the other short-term change we get, other than daily, is seasonal. So hopefully you're reasonably familiar with the concept of the seasons. This will be something that you've covered in science and previously in school. So we get seasonal weather because of the changes in solar intensity that we receive, and this is because of the tilt of the Earth's axis. So you can see down here that the tilt is around about 25.5 degrees. This does vary, it does, but that's not something we're really to get into. But we can see that over here, the northern hemisphere is tilted towards the sun, so we are in full summer. Days are long in the northern hemisphere, nights are short, and so therefore we're going to get a lot of plant growth in the northern hemisphere on the land. There's going to be long daylight hours, and we experience that every year, where all the trees, the deciduous trees, get their leaves, and the grass starts to grow much more rapidly, and therefore we've got carbon being stored in the biosphere during that time period. And then we go via autumn to winter, and at the winter period we're going to have a lot less evaporation. We're going to see a lot less plant growth. Many trees drop their leaves, and even the trees that don't drop their leaves, they basically shut down. They're not doing any real activity. They're not significantly photosynthesizing. This is also why trees have rings. So the rings represent the annual change. So you get a kind of dark ring in the tree, which is where the growth essentially slows down. So in the northern hemisphere, the northern hemisphere tilts towards the sun during our summer and away in the winter, as I say. Southern England receives 5 to 6 times more solar radiation in June than in December. So it's quite a significant difference in how much solar radiation we're receiving. And as I've mentioned, in terms of the water cycle, we're therefore going to see less evaporation from the surface. But we're still going to see quite a lot of precipitation, largely because the dew point will be quite low at this time of the year. And so clouds will form very easily. And if we think about our water balance equation, therefore we're getting very little evaporation. And that's why we end up with quite a lot of flooding, because we end up with more water in storage because there's a lot less evaporation, which means that the only way that water can leave the drainage basin is through stream flow. And when stream flow gets overflowed, that's when we get surface storage and flooding. So just to put this 5 to 6 times into figures, we get 800 watts of energy per meter squared from the sun in southern England in the summer, and 150 in the winter. So again, that's going to affect evapotranspiration. That's the energy that's required for evaporation to occur. So carbon cycle variations are shown through net primary productivity. This is the way we refer to plant growth. So net primary productivity, plants are the primary producers. They're the ones that take in the sun's energy and they grow. And so what NPP means is basically how much a plant's growing. So in the mid to high latitudes, that's where we are. The photo period, the day length, and the temperature limit growth. So what that means is there's plenty of water in England most of the time, apart from when we're in a drought. So it's the only thing that's stopping plants growing is how much sunlight they receive and how warm it is. Whereas in the tropics, it's actually water availability generally that affects growth. So there's plenty of sunlight, it's always warm. So the only thing that's stopping any growth happening is if there's not water available at that time. So during the summer in the Northern Hemisphere, during our summer, there is a net flow of CO2 from the atmosphere to the biosphere. This can actually drop the average atmospheric carbon by 2 parts per million, which is a very small amount, so it's really not a very significant amount. And then this is reversed in winter. So this only happens when it's summer in the Northern Hemisphere. So to understand why this is happening, we need to understand what is the difference between the Northern Hemisphere and the Southern Hemisphere, and why would summer in the Northern Hemisphere result in a net movement of carbon from the atmosphere to the biosphere, but it wouldn't happen in the Southern Hemisphere. And to understand this, we need to look at the globe from the point of view of the poles. So we have the Northern Hemisphere and the Southern Hemisphere. And hopefully you can see the significant difference straight away. Basically, the Northern Hemisphere has an awful lot more land mass than the Southern Hemisphere. So the Southern Hemisphere is dominated by ocean, and the landmass it has, Antarctica, is covered in ice. Whereas the Northern Hemisphere, huge areas of this land is covered in forest. Okay, all of the northern parts of Europe and Russia and Canada have vast forests. So during the summer, the trees are growing and they're absorbing carbon. And then during the winter, that carbon is gradually released, or it's certainly not being absorbed in the southern hemisphere in the same way. So there's not the same photosynthesizing happening in the southern hemisphere to the same degree. Now, obviously, the southern hemisphere has the Amazon up here, and it has various rainforests. So Australia has some rainforests, and Africa has some rainforests, but it's still not nearly as much land as we see in the northern hemisphere, and that's why we get this difference. Okay, so we want to have a go at drawing a graph. So hopefully you have some graph paper. If not, you may be able to do this using something like Excel. It will be a bit challenging, so it might be easier to do multiple separate graphs if you're using a computer rather than trying to put them all on one, but it is possible. It's a bit of a challenge. So on page 128 of the textbook, there is an area at the bottom called Skills Focus, and it gives you a table with the average flow of a river, the rainfall in the area, and the sunshine hours. There is also a table slightly higher up the page, table 414, which has evapotranspiration for certain months of the year, April through September. So what you need to do is have a go at representing this data on a graph. So just point out first of all, this bullet point number 2 here, that the river flow, the evapotranspiration, and the sunshine should all be shown as lines, and the rainfall should be shown as bars. Okay, and what you want to do is try and analyze, is there any relationship between these pieces of data? Okay, so what we should want to see is our sunshine hours having an influence on flow? Is rainfall having an influence on evapotranspiration, or vice versa? And that's what we want to be trying to establish, trying to understand. And then we've got an extension, so discuss other influences in the drainage basin hydrological cycle that could impact the river. So that could be to do with humans and what they're doing. Okay, so to give you an idea, this is a starting point that I've created. So just to kind of show you what it should look like, what I first of all highlight is, if you're using graph paper like this, if you're using A4 graph paper, I would just copy these axes as you see them here, because this is how it all sort of fits nicely on. So we've got 2 different y-axes. We've got sunshine hours over here on the right, and then we've got the other 3, rainfall, evaporation, and flow on the left. And so that by doing it that way, it all fits on the page. Don't forget rainfall as bars, sunshine as a line, evaporation as a line, and flow as a line. As I mentioned, the evaporation data starts in April and runs to September. So this black line that I'm drawing here would only go up until September. After that, there's no more data for it. So do have a go at trying to draw that. If you've got some graph paper, if you've got a printer and you don't have any graph paper, you could always print off a sheet with graph lines on it, or like I say, have a go at doing it using something like Excel. It's good practice. It's good to sort of figure out how to present data, because ultimately with regards to things like coursework, you're going to have to kind of grapple with how to present data at that time by yourself. So it is worth getting used to the challenge. So longer term changes in the water and carbon cycle. So this is showing carbon dioxide parts per million and temperature change over the past 400,000 years. And what we have is various sections. So just sort of draw off the sections here. So each of these intervening areas are glacials. So we've got 4 glacial periods, quite long glacial periods over the last 400,000 years. So at this point, temperature dropped on average to -8 degrees compared to our normal average at the moment of sort of +2 to 4 degrees average temperature of the planet. And we see a large drop in parts per million of carbon as well in the atmosphere. So multiple glacial periods historically. So when we think about long-term change, we want to think about what impacts these glacials will have had on the water and the carbon cycles. So what we'd be looking at is, in the water cycle, a huge flux, a huge transfer of water from the hydrosphere to the cryosphere. So a lot of the water that is in the ocean being stored on land in the form of ice. So huge parts of the globe would have been covered in ice. We would have seen ice spread out from the poles, which is where we get our glacial landforms from. It's all of these glaciers. We see a massive sea level drop from this, so 100 to 150 metre drop in sea level. This would have led to the UK being linked with the rest of Europe by land, and it would have allowed animals to cross into England from Europe, and all kinds of other processes would have occurred during that time. So biospheric water and carbon stores shrink as the glaciers move equatorwards, so towards the equator, and destroy forests and grasslands. So as the glaciers move further and further towards the equator, we're going to get a lot less water and carbon stored in the biosphere, but we will get quite a lot of carbon stored in permafrost and trapped under the ice. So as the glaciers move, they will be trapping forests beneath them, things like this. Essentially, the water cycle will just slow way down. So you can talk about this is really significant in terms of a change, that the water cycle would be so much slower. There's basically the water cycle is run on energy and energy from the sun, and a glacial period represents a time of very low thermal energy, which means that that process of evaporation is happening very little, and it's evaporation that kind of gets the water cycle going. It's the water evaporates, and then it has potential energy in the clouds and in the atmosphere, and it falls and it flows over the land. So without that evaporation happening regularly, we've got a very slow water cycle. With regards to the carbon cycle, it's a little bit more complicated. We understand it not quite as well, but atmospheric carbon drops dramatically, and scientists aren't 100% sure why. So tundra replaces forests, and a huge amount of carbon is stored in the permafrost, which may play a part. Something else that could be causing this drop is, as we've talked about before, how soluble carbon dioxide is in water is affected by temperature. And the colder it is, the more soluble CO2 is in water. So as the temperature drops, water can absorb more carbon. So that may be where some of the atmospheric carbon is going. It may be that the water on the planet that hasn't become ice is able to absorb large amounts of carbon. Also, a lot of the carbon may be being stored, as we say, within the permafrost. But either way, we get a lot less carbon in the atmosphere. We also get a lot less water in the atmosphere due to a lot less evaporation. Okay, so we also need to know about how climate change is monitored and about how the impacts of climate change is monitored. So we've got a few different ways that this is done, things like monitoring global air temperatures, sea surface temperatures, sea ice thickness, and rate of deforestation. So we need to know how to do this accurately, reliably, and efficiently. So what I want you to do is have a look at page 127, table 4.13, and there's about 7 examples there. And I want you to make some notes on 3 of them. So choose 3 that you think you can remember. And these are all about remote sensing, meaning sensing change from a distance, not actually physically going there and measuring it, but doing it from a distance. And we generally use satellites for this. So for example, measuring the area of sea ice you could do with a satellite quite well, but there's a range of other ways of doing it. So there's things like sea ice temperatures are measured by looking at the amount of radiation being emitted by the ocean surface and the amount of sort of heat energy coming off the ocean. And just to finish off this section, we've sort of finished our learning on section 3 of the topic, is have a read through pages 126 to 130. A lot of it is what we've covered today, but just sort of have a read through and make sure that you've not missed anything and take any additional notes. Like I say, it is what we've looked at during this PowerPoint, but it just gives you a chance to go through it a bit at your own pace. And at the start of next time, we'll go through the review questions on page 130 and get started on section 4.